Hello. This week, in the first three lectures, we had talked about analysis using pseudo-rigid body modeling. In the next three lectures this week, we will discuss synthesis. By synthesis, what we mean is designing a compliant mechanism consisting of one or more elastic beam segments and trying to get the functional specifications met. We will discuss what those functional specifications are and how to set up the equations and how we will solve them. Today we will focus on understanding the equations involved in synthesis, and in the next two lectures we will consider how to implement them and synthesize by way of examples a few compliant mechanisms. So, let us look at the synthesis using pseudo rigid body modeling. So, let us recall that when we have a compliant mechanism, let us say in this case we have taken a 4 bar linkage which has torsion springs at its 4 joints, and we want to see if we can synthesize a mechanism such as this for given specifications of some functionality. Okay. So, when we have a 4 bar linkage with 4 torsion springs, we already understand that it is a pseudo rigid body model of a compliant mechanism. A compliant mechanism may have only one elastic segment or 2 or all 3 as well, whichever way that is, as long as the validity of the pseudo rigid body model is true, we can create a model such as this, where there is a 4 bar linkage where we have a torsion spring at each of the 4 joints. It can be more than a 4 bar linkage also, but we are taking example of a 4 bar linkage now. And when a force is applied such as this F here, it is going to move from this original configuration. So, this is our original or undeformed configuration. By original, what we mean is that it is and deformed to the moved configuration. See, moved or what we call deformed, which is the correct word here, not just displaced, because there will be an elastic segment or 2 which will be deforming elastically, and that is when we have this moved configuration with application of force, and at each joint we have the rotations which are given by mu1, mu2, mu3 and mu4, which we can write. Okay. When you have something like this, we discussed how to analyze them, but now let us talk about actually synthesizing them. Whenever we synthesize a mechanism, be it a rigid body mechanism or a compliant mechanism, we should always worry about equations and unknowns. Unknowns are the ones that are the design parameters here. Those are the ones that we need to find, as opposed to in the analysis most of these are already known and we just need to find the remaining one, that is analysis, right. In the case of synthesis, we have to determine, for example, the length of the bodies and torsion spring constants, initial configuration, because that is also an unknown, and then rotations in all configurations. Normally analysis, given the first 3, you can find rotations in all configurations. That is what we discuss in analysis. In the case of synthesis, these are the first 3 are also unknowns, and as we will see, some of the rotations in all configurations will also be unknowns. Okay. Once we know what the unknowns are, they become our variables or parameters in our synthesis problem. They are the unknowns. In order to solve for them, we need equations. There are 2 kinds of equations, as we already know from analysis that we discussed in the last 3 lectures. There are kinematic equations, or what we call loop closure equations. We close the loop, as we will see now, and also the force displacement relationship or relationships, because if there are more than 2 or 3 positions that we want to synthesize for, there will be a number of force displacement relationship that we need to take into account. That gives an equation. So, the first one is kinematic equation, The second one is elastostatic equation. Elastostatic equation, which is the equilibrium equation or force displacement relationship. On the right hand side we have the force, and on the left hand side we have rotation, which is the displacement here, right. So, we need to find this rotation theta, on which the psi and beta also depend. So, we have force and rotation equilibrium equation for the example we had considered in the analysis case. So, we will have this elastostatic equilibrium equations. Now, let us look at the loop closure equations, or what we call kinematic equations. So, these are kinematic equations. We had used that in the analysis in the context of computing the sensitivity coefficients, that is d beta by d theta, d psi by d theta, that is coupler angle and output angle. At what rate do they vary with respect to the input crank angle, which was theta. For that we had used loop closure equations. Now, we will understand and use these loop closure equations in the context of synthesis. For that we need to introduce a concept that uses complex numbers, which makes it easy. So, they are complex numbers which make our job easy, as we will see. So, let us consider without springs first, because kinematics does not need to include that. Let us take a 4 bar linkage with 2 fixed hinges and 2 floating hinges. Now, what we do is to represent this using complex numbers. So, let us take the coordinate system here. You can take it anywhere you want, but right now we will take it at the pivot that is given. So, we have x axis, y axis. Now, this one is a vector, right. Let us call that Z2. When I write Z2 in this manner, in a script Z fashion, what I mean is that it is a complex number which will have real and imaginary parts. So, let us indicate that this angle is, let us say, theta 0, and length of this is let us say L2, as we had done earlier. Then Z2, if I take the origin at the point where we have indicated, that is this point, I can write Z2 as a vector or as a complex number. I can write it as L2 cosine theta 0, that is the real part, and then L2 plus L2 sin theta 0, that will be the complex part. I will put I. Okay. So, we have written the input crank as a vector and represented that using a complex number. There is a nice reason for why we want to use complex numbers, but let us first write all the vectors as complex numbers. So, Z2 we have. Similarly, I can have from here to here Z3. Okay. So, Z3 is basically the complex number that represents the vector indicating the coupler. Between the input and output we have the coupler, that is Z3. Okay. And we can also write Z4, which is output crank vector, that has again real and imaginary parts, and we can include the bottom one, let us call that Z1, that L1 we call it Z1. Okay. So, each of them, if we know the angles, let us say I call this angle psi 0, I call this angle beta 0, we can write. So, we can write Z3, if I indicate this length by L3, this is L4 and this is L1, I can write Z3 as L3 cosine beta naught plus I L3 sine beta naught, and Z4 as L4 cosine psi naught plus I L4 sine psi naught, and Z1 is easy because it is just L1, and there is no imaginary part because there is no y component for Z1 vector. So, it will be I times 0. Okay. So, that is basically not there, right. Now, we have the 4 vectors represented like complex numbers. So, now I can write what we call loop closure equation, that we can see. Let us say I start with Z2, I am going from, let me indicate them as A, B, C and D. I move from A to B, that is Z2, plus I move from B to C, that is Z3, and then I move from C to D. The D to C is Z4. I am moving from C to D, that will become minus Z4, and that will be equal to Z1 or minus Z1 equal to 0. We are closing the loop. That I am going from A to B, B to C, C to D. I could have moved from A to D directly, that would be Z1. So, this is our loop closure equation. So, we will just simply closing the loop. This is the loop closure equation. Okay. At this point, you may wonder why we are using complex numbers to indicate vectors. Why could have just used vectors, right? I could have called V2, V3, and I could have called V2 plus V3 minus V4 is equal to V1, but why are we using complex numbers? There is a significant advantage for using complex numbers when we consider this one in a moved configuration. By that, what I mean is that if I have, let us say, if I have, let us say, a vector like that, which is represented with some complex number z, okay, between 2 points, is a relative position vector between 2 points. Now, if this were to rotate by some angle, let us just take it as alpha here. What is this rotated angle? Let us call that Z R, which is to indicate rotated. It turns out that Z R can be simply written as Z multiplied, that is a complex number, multiplied by another complex number, which is e raised to I alpha. Okay, it is as simple as that. So, when we have this z rotate by an angle alpha about z axis, the rotated complex number indicating that rotated vector can be simply given as z times e raised to I alpha. We follow the complex number multiplication rules here. So, z star e alpha, by that what I mean is that z star e raised to I alpha. E raised to I alpha, as you know, is I will just write here, e raised to I alpha is cosine alpha plus I sin alpha. So, that is also a complex number. Okay. So, when you multiply these two, I get the rotated vector. That is why we use complex numbers to represent vectors, and it is very useful in synthesis, as we will see shortly. So, if you want, you can work it out. If I have a vector, I rotate it by an angle alpha, then you can see what these components are. So, let me draw those components. So, this will be the y component, this will be x component. What will they be relative to the original one, where that would have been the x component, that would have been the y component? How are they related with alpha? it will be related in this manner. You can work it out and check. Now, what is advantage for us? If I consider a rotated configuration for this, let us say this thing has moved to another configuration, all I need to write is Z2 into e raised to I, whatever angle that is, which we had said rotation is, we had called it mu 1, okay, plus Z3 e raised to I, we had called it let us say I think the mu 1 mu 2 was rotations at this point. Here rotation would be just beta, right. So, we can just write it as beta minus beta 0 rotation angle, okay, because here mu 1, if you recall, mu 1 was theta minus theta naught. So, that is the rotation, okay. But here we have to write the rotation of the coupler body, body that we have, that will be I raised to beta minus beta 0 and then minus Z4 times e raised to I, that would be psi minus psi naught, that is the rotation of the output one, psi minus psi naught, that will still remain Z1, right. So, when we have rotated configuration, so I do not want to draw it here because it will become very clumsy. Rotated configuration, each vector we can write simply by using these complex numbers Z2, Z3 and Z4 multiplied by e raised to whatever the corresponding rotation is, we get the equation that we can do for any position. So, getting loop closure equations become very easy, okay. You may still not see the advantage other than saying that we have this easy way of writing rotated configurations. We can also do this with vectors. So, where do we again gain? We gain because all the operations involved here are complex number operations which can be easily implemented in any programming language, but there is more to it that we will see as we go along, okay. So, now before we use this loop closure equation that we just wrote, let us talk about what kinds of synthesis problems we want to solve. In kinematics, in the kinematics literature, there are three kinds of synthesis problems known as function generation, path generation, rigid body motion generation. Sometimes people leave out this rigid body, but it makes it clear if you say that in this manner. What is function generation? Function generation is if I have a 4 bar linkage like that with 2 fixed pivots, there are these moving pivots here, okay, 4 of them. The rotation, if I indicate that as theta, if I indicate this as psi, in function generation what I want is that somebody would prescribe, or the problem on hand they may say psi and theta have to follow a certain function, okay. These were the functions. So, here psi is a function of theta. So, this is the function, okay. So, somebody wants a function of this kind, then you need to synthesize the lengths of the bodies and the initial configuration, so that you get psi theta. In the case of compliant mechanisms, because they cannot move unless you apply a force, we can say this as a function generation, where we can say if force is the input here, I can say theta here has to be in some form, okay. This is the normal kinematics problems, kinematic synthesis of function generation, kinematic synthesis for function generation. You are basically generating a function. In fact, before digital computers came, if you want to generate a function, it had to be done analog, sometimes mechanically. So, that is where this function generation term comes. So, somebody wants a function of certain kind, sine, cosine, in fact there are beautiful mechanisms that can do even Fourier expansion of a given function. So, they can synthesize or analyze a function for Fourier expansion. So, in general it is known as kinematic function generation. Okay. Now, if we have theta versus f, that becomes our elastostatic function generation, elastostatic function generation. Okay. So, we will be looking at that type of problems today. The third is the motion generation, where if I have a triangle that we are talking about coupler, if let us say original one is A, B, C like that, let us say it moves to a new configuration which B comes here, let us call it B prime, A prime here and C prime. So, what we see is that the B point has moved along a path, at the same time the rigid body is rotating also. So, if you do that, we call that a motion generation problem, rigid body motion generation problem. We have to guide a body from position to position as prescribed by an application. Sometimes we will have the planks in a chair in a classroom, you take it out and you flip it. So, sometimes there is a hinge, sometimes the whole thing comes like a rigid body and from folded configuration to a deployed configuration. So, such things we call motion generation problem. So, there are 3 types of synthesis problems. So, what we will do now is just begin writing the equations for a function generation problem. So, let us say if I have 4 bar linkage, and let us not forget that we have springs. Okay. So, we have the 2 pivots and we have the springs, but generality let us say that there are these torsion springs at all 4 joints. Okay. So, let us also indicate our unknowns, because we have not synthesized it. So, Z2 will be unknown and so will be Z3 and so will be Z4 that we have, and then this also which we called Z1. Okay. The initial angle is embedded in Z2 as we saw. Z2 already has this theta 0, so is beta 0 and so is psi 0, and then we have this torsion spring constants kappa 1, kappa 2, kappa 3, kappa 4. Okay. So, let us count our unknowns. Our unknowns, when I say I need to synthesize this 4 bar linkage Suraj body model, our unknowns are Z1 and Z2, Z3, Z4 and these kappas, kappa 1, kappa 2, kappa 3 and kappa 4. How many are there? Let us say the scalar unknowns, because when you write complex number, when you say that is not known, there will be 2 unknowns, but here the way we are taking the xy coordinate system, Z1 will have only one scalar unknown, because it is already known to be on the x axis, y component is not there. In general, you can orient whichever way, that does not matter for function generation, because we are only worried about the angle theta and angle psi, whichever configuration it is, it does not matter. Okay. So, that is why we count it as 1, and then here we have 6 unknowns, because each of these Z2, Z3 and Z4 have 2 unknowns, scalar unknowns in them. There are 6, and then here we have 4 scalar. So, total we have 11 scalar unknowns. Okay. For function generation, what is given, what is known, that also we should write. what is known? What do we think that we know? So, first of all the forces. Okay, we start from the given configuration, we go to the first configuration, which I can say there is F1 force that takes you from original configuration to the first configuration, and there will be F2, F3 and so on. Okay. So, Fn configuration. So, this is the force, the other unknowns, knowns, because that is what people will say, I want to apply this much force, you should go to some angle, right. So, for taking the first configuration, okay, so taking the first configuration to the second, okay, and this is from second configuration to third and so forth, right. We have the knowns, and then we may say it has to happen, that is these are the forces given, but then when you say function generation, we say that there should be this angle, okay, which we can call theta or mu. It is probably better if we call it mu. This is mu 1 we had called, let us say the input angle. I would like to have this mu 1, okay, from the first configuration, second configuration and so forth. In fact, mu 1 other number becomes a problem, let us just call it theta itself, okay. There is a theta 1, there is a theta 2 and theta 3 and so forth, theta n configurations. Theta 0 is our original one, that goes to theta 1, that goes to theta 2, that goes to theta 3 and so forth. In other words, what we are asking is a function theta as a function of f, which is some curve. We are saying if I apply a force F1, okay, in fact I should not make it 0. So, let me change this curve. Let us say I start from somewhere. So, this becomes our theta 0 when there is no force. When I apply F1, I want theta 1, when I apply F2, I want theta 2 and so forth. So, I am taking these points, okay, original point and some more points. So, this could be let us say Fn, this is F2, okay. So, this is a function I am specifying. I may not give a function as an expression, but I may give you for sure what thetas I want for different f values, okay. So, we know forces and we know thetas, those are known, and in the initial configuration and the spring constants are our unknowns. So, you have to count the unknowns and try to get as many equations as needed to solve for these things. So, equations if you look at we will have. So, now let us recapitulate unknowns. Unknowns will be this initial configurations Z1, Z2, Z3, Z4 and the 4 spring constants. Z1 will have only one scalar, others will have 2 each, so that becomes 6 and 4 total 11, and the knowns are forces and these rotations that we want. There is a correspondence between the input force can be anywhere. So, it can be a force here, there, does not matter, a force and the corresponding rotation of the input crank. So, theta versus f. So, those are knowns to us, okay. For finding unknowns we need equations. What are our equations? Our equations are of course loop closure equation. We had what we had written Z2 plus Z3 minus Z4 is equal to Z1. How many equations are there? I will say the scalar equations. How many are there? Because it is a complex equation, you can equate real parts and imaginary parts. There are 2 equations, okay. Now, we write in the moved configuration Z2 e raised to I theta minus theta 0 plus Z3 I e raised to I beta minus beta 0 plus minus, because of the way we wrote that vector, minus z4 e raised to I psi minus psi naught, that will still be equal to z1. Now, how many equations are there? It has also two equations, real parts, imaginary parts. So, this one, let me call it actually the first position, theta 1 beta 1 psi 1, rotated by theta 1 beta 1 and psi 1. Okay. Those are two equations for us. But then we also have the force equation, F1 equal to F of theta 1. This F is given to us, theta 1 is also given to us, but this function, which was the force displacement relationship, will involve all the body lengths and angles, torsion spring constants and so forth. So, how many equations is this? It is 1. Okay. So, we now have from the first configuration, there is no force equation, because there is no force, so it is just 0 and angles are not moving. So, there are two kinematic equations alone, but for any other position, for the first position we have two kinematic equations and one force equation, right. We had counted that we have 11 unknowns, now we have only 5 equations, right. That is good actually. If we have more unknowns than equations, it is a happy situation, because you can assume whatever is the excess number of unknowns. So, if you go back to the previous slide, out of these unknowns, 11 of them, now we have only 5 equations, 5 scalar equations, 11 scalar unknowns. I can assume 6 of them, right. I might as well assume these 6, that is, I choose Z2, Z3, Z4, meaning a configuration of the 4 bar to begin with, and then I will use those 5 equations that I have to determine kappa 1, kappa 2, kappa 3, kappa 4 and Z1, which has one scalar unknown. Okay. In fact, if you do that, that will be a bit of a problem, because the kappa 1, kappa 2, kappa 3 are going to be in this nonlinear equation. Okay. These are also nonlinear because angles are there, but you will see the advantage of using complex numbers. Why I would call them linear, because they are linear in complex numbers when you arrange them in a particular form, whereas this one remains a scalar equation, not a complex equation, and this is non-linear. The force displacement relationship is non-linear. In any case, if we just count the number of unknowns and equations, here we have 5 equations and we have 11 unknowns. So, we can assume any 6 of them freely. But now let us say I go to the next position, Z2 e raised to I theta 2 minus theta 0 and Z3 e raised to I beta 2 minus beta 0 minus Z4 e raised to I psi 2 minus psi 0, that will still be equal to Z1. That will give me 2 more equations, and then I will also have F2 as a function of theta 2, that is one equation. So, we have total now 5 plus 3, 8 equations. Okay. Now, I have 11 unknowns and can count how many are there, but we should note that when I wrote these unknowns, I did not include a few extra unknowns that are coming. Okay. So, let me use a different color to say that over here extra unknowns are there, which are this theta 1, beta 1 and psi 1, right, because those were not in the initial configuration. So, unknowns are also increasing, and then here also we have this theta 2, beta 2, psi 2. Okay. So, we have to see the number of equations and unknowns and try to balance the equations and unknowns to see how many equations we get based on how many positions we are considering, how many configurations. So, this is the first configuration, and then we have second this is 0th configuration. Do not be confused by this using 1, let me call this original configuration or 0th configuration. So, this is the original configuration, and then it is the next one and next one. We have to see how many unknowns and equations are there and try to come up with the appropriate number of equations and unknowns and try to balance the number of equations and unknowns. If unknowns are more than the number of equations, then you can assume some of the unknowns, but if the unknowns are dominated by the number of equations, there will be over constrained system, and that we cannot solve. Okay. We will see this by way of an example problem we will consider, so that we can first count number of equations and unknowns and then work through it. Okay. That we will do it in the next lecture, which is a continuation of this lecture. Thank you.